Dear students, in the last class, we have discussed about the valence bond theory of the coordination compounds. So, we have also studied the valence bond theory applicable to the various complexes and finally the limitations of valence bond theory. So, today let us study the another theory called the crystal field theory. This is the crystal field theory was developed by H. Bethe and Van Vleck in 1935. This theory explains bonding and properties of coordination compounds more successfully than the valence bond theory. According to this theory, bonding between a central metal ion and its ligand arises from purely electrostatic force of attraction and also the electrostatic interactions. If the ligand is an anion, the attraction towards the cation is as that between any oppositely charged particles. That is the electrostatic force of attraction. If the ligand is a neutral molecule such as ammonia or water, the negative end of the dipole is attracted towards the central positive ion. Considering the metal ion and the ligand as the point charges Q1 and Q2 separated by a distance r, the metallic ligand bond energies for various complexes can be calculated using the Coulombic law, that is bond energy is equal to minus Q1 upon Q2 upon R. For non-transition metal complexes, the theoretical and experimental bond energies are almost equal. For transition metal complexes, the theoretical values of bond energies are too low as compared to experimental bond energy values. This is due to the orientation of d orbitals in space. There are two types of d orbitals, namely T2g and Eg orbitals. T2g orbitals are dxy, dyz and dxz, wherein double dumbbell shaped lobes lie in between the axes. Eg orbitals are dx square minus y square and dz square, wherein double dumbbell shaped lobes lie along the axis. The separation of 5d orbitals of the metal ion into two sets having different energies is called crystal field splitting. This concept makes the basis of crystal field theory. The energy gap between T2g and Eg sets is denoted by delta and delta naught for octahedral complexes and delta T for tetrahedral complexes. It is also denoted as 10 dq. This is called crystal field splitting energy, commonly known as CFSE. The coordination compounds with coordination number 6 and coordination number 4 are most stable. The coordination compounds with coordination number 6 exhibit octahedral geometry. The coordination compounds with coordination number 4 exhibit two geometries, namely tetrahedral and square planar. In all these complexes, the splitting of d orbitals is different. Now let us study the splitting of d orbitals in octahedral complexes. In an octahedral complex, the coordination number is 6. The metal ion is at the center and the ligands occupy the 6 corners of the octahedron. In the free ion, where there are no ligands, the electron can occupy only one of the d orbitals because all are of the same energy. Such orbits are called degenerate orbitals. We know that there are 5 d orbitals, out of which the 2d orbitals, namely dx square minus y square and dz square, they are also called Eg orbitals. These are oriented along the axis, and remaining the d orbitals, namely dxy, dyz and dxz, which are also called T2g orbitals, are oriented in between the axis. In case of octahedral complexes, as the ligands approach the central metal ion along the axis, the energy of the Eg orbitals increases much more than the energy of the T2g orbitals. This is because of greater repulsion along the axis, which further results in increase of energy. Here I have shown the crystal field splitting in octahedral complexes. In the degenerate state means a normal state. So before the entry of the electrons, all have the same energy and they have a minimum energy. When the ligand approaches to the metal ion, so these orbitals gets excited, and it is also called hypothetical degeneracy of all the orbitals at higher energy levels. And when the ligands approach still closer, as we know, the ligands approaches along the axis, the Eg orbitals are also along the axis, therefore Eg orbitals gets more energy than the hypothetical orbitals, and T2g orbitals gets lesser energy than that. The word G refers to here the gerade. The gerade means the metal ions which have the center of symmetry, the complexes which have the center of symmetry, these are known as the gerade orbitals. Hence the word Eg and T2g. Crystal field splitting is measured in dq. The difference between Eg and T2g energy level is called 10 dq or delta naught. Delta naught means crystal field splitting in octahedral complexes. In octahedral complex, the energy of the T2g orbitals is 4 dq or minus 0.4 delta naught, and the energy of the Eg orbital is 6 dq or plus 0.6 delta naught with respect to hypothetical degeneracy of orbitals. Go through this diagram properly. Now let us know what is this crystal field stabilization energy. We know that an electron always prefers to occupy an orbital of a lower energy. In an octahedral complex containing 1d electron resides at T2g orbital. This orbital has less energy of minus 4 dq or minus 0.4 delta naught than the hypothetical degenerate orbital. Thus, the complex will be 4dq more stable than predicted by the pure electrostatic theory. The decrease in energy, which is known as 4dq, this is called crystal field stabilization energy of the complex under consideration. The lowering in the energy of a transition metal ion in a given ligand environment due to crystal field effects is known as crystal field stabilization energy. I repeat, the lowering in the energy of a transition metal ion in a given ligand environment due to crystal field effects is known as crystal field stabilization energy. Crystal field stabilization energy are calculated by considering the splitting into a T2G orbital. CFSE is 4dq. For each electron entering into EG orbital, the destabilization energy would be 6dq. Working on this basis, it is possible to calculate CFSE for various metal ions in octahedral geometries. Now coming to the another point known as pairing energy. The energy required to pair the electrons with one another is called pairing energy. It is related to the energy of the electrostatic repulsion amongst the d electrons. If the 10dq or delta naught is greater than the energy of the electrostatic repulsion amongst the d electrons, or 10dq is greater than pairing energy, in such cases the pairing of electrons in a T2G orbitals take place before going to the EG orbitals. Such complexes have less number of unpaired electrons. These complexes are called low spin complexes or strong field complexes. If delta naught or 10dq is less than pairing energy, in such octahedral complexes, the unpaired electrons enter both in a T2G and EG orbitals and then pairing takes place. Such complexes have more number of unpaired electrons. These complexes are called high spin complexes or weak field complexes. Now here, this is a table how to calculate the crystal field stabilization energy for various configurations in octahedral system. Now, as we have studied, in octahedral system, we have the low spin or strong field ligands, which are also known as spin paired complexes. And also we have high spin or weak field ligands, which are known as which are also called the spin free complexes. Now let us study how to calculate the crystal field stabilization energy in case of the low spin or strong field complexes. Coming for the complexes with D1 configuration, they contain one unpaired electron. Each unpaired electron is having a spin half. So therefore we have a spin half, and the distribution of electrons in D1 system is T2G1 EG0. Now the electron resides at the T2G orbital. Therefore it is decreased by the energy 4dq. Therefore its crystal field stabilization energy is minus 4 dq. In case of D2 system, it contains 2 unpaired electrons. Therefore, the spin will be half plus half becomes 1. The electronic configuration becomes T2G2 Eg0, which contains 2 unpaired electrons in the T2G orbitals. So each contributes minus 4 dq. Since 2 electrons are there, it becomes minus 8 dq, the CFSE value. Coming to the D3 system, which contains 3 unpaired electrons, the spin will be half plus half plus half, which is equal to 3 by 2, and the electronic configuration will be T2G3 Eg0, which contains 3 electrons in T2G orbital. Each contributes 4 dq. 4 into 3 will be minus 12 dq. Coming to the D4 system, which contains 4 electrons. Each electron contribution is the what you can say the half. So therefore, since here in this case only 2 unpaired electrons are there, its spin value will be 1. And in this case, the T2G4 Eg0, the electron pairs in the T2G orbitals, hence it is known as strong field ligand. The energy difference is more. In this case, since 4 electrons are there in the T2G orbital, each contributes 4 dq, hence it becomes 16 dq. And this contains 1 paired orbital, hence we write plus p. P refers to pairing energy. In a D5 system, it contains 1 unpaired electron. Its spin will be half, and it contains 2 paired electrons. So the totally 5 electrons are there in T2G. Each contributes 4. Therefore, 4 into 5 is minus 20 dq, and 2 lone pair electrons are there. So plus 2p, pairing energy. When we take the D6 system, all are paired up. So here in this case, the unpaired electrons is also 0 and the spin value is also 0. And since the 6 electrons are there in the T2G, 6 into 4 will be the 4 into 6 will be the 24 minus 24 dq, and it contains 3 lone pairs of electrons. Therefore, it is the pairing energy will be 3 into p. When we take the D7 system, it contains the electronic configuration T2G6 Eg1, which shows that it contains 1 unpaired electron. Its spin value will be half, and that Eg electron is having plus 6 dq. Therefore, T2G is having 24 plus minus 24 plus 6 will be equal to minus 18 dq, and it contains 3 lone pairs of electron plus 3 into p. That is, p is the pairing energy. Similarly, for D8 system, it will be minus 12 dq plus 3 pairing energy. For D9 system, it is minus 6 dq plus 4 pairing energy. And for the D10 system, all gets paired up. So the value will be 0 dq plus 5 pairing energy. The crystal field stabilization energy is calculated as I have explained. That is by the equation minus 4 into x plus 6 into y dq plus n into p, where x and y are number of electrons in T2G and Eg orbitals respectively. P is the pairing energy and n is the number of paired electrons. In case of strong field system, the complexes, the 10 dq value is greater than p. Therefore, the energy difference between T2G and Eg is very high. Here also I have explained in the similar, I have shown here the Eg orbitals and T2G orbitals. Eg orbitals are dx square minus y square and dz square orbitals which lie along the axis, and dxy, dyz and dxz orbitals which lie in between the axis, and the splitting of energy levels in the formation of an octahedral complex ion, that splitting also I have shown and explained here. Now, crystal field theory for octahedral complexes. Here in the crystal field theory for octahedral complexes is the two examples I have shown for the iron. So one is the FeH2O6 times 2 plus. Here water is a weak field ligand. When it is a weak field ligand, the difference between T2G and Eg is less. It forms high spin complexes. In case of ferrocyanide ion is a strong field ligand, so which results the energy difference between T2G and Eg is high, which results the low spin complexes. Crystal field splitting energy is also explained in this table. Here I have defined what is this crystal field stabilization energy.